So what's the Dynapower solution to this situation, to this scenario?
We pretend to be like a conventional generator. We
With
behave like a conventional 20th century generator.
with a software and battery coupled solution.
Yeah, exactly. So we take our bidirectional energy storage inverter, we
Yeah.
overlay a very tight software control on top of it, which is actually a grid forming software control. It is synchronous grid forming. And that's a fairly new term, so I'll explain it a little more. Rather than being grid forming in a pure off-grid scenario, like
Hmm.
the microgrids that we were talking about,
Yeah.
in a synchronous grid forming scenario, we're actually constantly operating the inverter in what's called a voltage source mode. So we are actually contributing and driving that AC waveform rather than being a grid following inverter, which is just seeing a waveform and latching onto it and injecting current. That's a current source mode from a grid following inverter. In a grid forming inverter, we're in a voltage source mode, and we are helping to build upon that waveform. And in a virtual, what we call virtual inertia, is basically it's a software control where we're emulating the physics, the Newtonian physics of that rotating mass. Because with an inverter, it's basically, we're digital. The old generators are analog. We have a lot more ways that we can operate in a digital world. We can adjust that waveform between active and reactive power quite significantly, and in doing so, we can create the same exact type behavior that a
Yeah.
spinning generator would, conventional fossil fuel generator. And so it's a really important technology to help create enough level of inertia on the power grid to prevent catastrophic collapse that can be substantially exacerbated by large scale deployment of grid following type inverters, which is mostly what we have out there these days. So we do it with an inverter with software controls, and then we need a battery, of course, connected to the inverter as a DC source. So it's always a captive sort of reserve of capacity to create that stability. But that's how I like to describe it. What the grid forming, fundamentally the physics that we're creating, the problem it's really solving at the simplest level, it's basically just acting like a giant shock absorber. So when there
Yeah.
is a disturbance on the grid, we can absorb that with our basically how we're building upon the waveform. So that it doesn't prevent this catastrophic and rapid collapse due to a very sudden drop in rate of change of frequency. And what these systems are really trying to do is buy time.
Yeah.
That's really what because there are plenty of other backup types of systems, including fast frequency response, that our inverters are capable of delivering as well, as well as plenty of other inverters, because there's sort of market mechanisms that incentivize that type of control and behavior. But fast frequency response, key point, is not instantaneous. It takes
Mhm.
time to do fast frequency response, though be it less than a second, but
Yeah.
still in
Still.
the amount of time that we're talking about, the time scale that we're talking about to prevent a catastrophic collapse,
Yeah.
that's ages.
Yeah.
So what we have to do, because fast frequency response is basically, it requires the inverter to measure the signal, process it. There's computing happening, and then it needs to decide, how am I going to react to this signal, this measurement that I just took. Believe it or not, that cycle to calculate and react is wasting precious milliseconds that we
Yeah.
can't afford to waste when there is a drastic collapse. And so what's so cool about the synchronous grid forming and the virtual synchronous inertia is that we are doing that control without any processing time wasted. It's inherent into how we're operating the inverter. It literally behaves exactly like a rotating mass would. There is a slowdown, sure, but with a dampening factor, we can behave like this sort of slower and slower decelerization, buying us enough time by continuing to inject inertia into the grid, buying us enough time for these backup power systems to kick on and then take over and bring the frequency back up to a reasonable level. And so fundamentally, that's what we're doing with inertia, it's also, we're able to inject strength into the electric grid as well. And that's grid strength. It's sort of a not a well-defined term, but there is a measurement that we use for it called SCR, or short circuit ratio.
Mhm.
And the short circuit ratio is basically it's a measurement of the relationship between the short circuit apparent power when there is a line, like a triple line fault on that particular node in the electric grid. I don't want to get too technical here, but basically the way that we measure the strength of the electric grid is if you have an SCR, a short circuit ratio of 3 or higher, that's a strong grid. Between 2 and 3 is really defined as a weak grid, and less than 2 is a very weak grid. And so why this is an issue is that in a very weak grid, you couldn't even connect a solar inverter or an energy storage inverter. It oftentimes won't even latch. Even the
Mhm.
grid following inverter wouldn't even be able to connect and inject active reactive power onto that grid because it is so weak. It's so unstable. I mean, I will plug Dynapower's inverters and say that Dynapower's inverters are capable of connecting and operating on grids that are less than 2 short circuit ratio,
Wow.
which is puts us into the very weak range. But it's tricky, and so yeah, what do we do? With synchronous grid forming technology, we can actually, because we're building upon that waveform, we can literally inject strength into the grid at that interconnection point and bolster it, which therefore allows us to connect more and more solar and batteries, other inverter-based resources to that grid.